So in this video, we are going to talk about the rate law and how to calculate it, how to determine it for any given reaction. So we've discussed the idea of a reaction rate, and we know the rate is the speed of a reaction. We know that the rate of a reaction is dependent on the concentration of reactants as well, how much of each reactant you have. So for example, if we have this reaction here, A plus B produces C and D, where these are our coefficients, the lowercase letters are coefficients, we can experimentally determine an equation. The rate law is an equation that tells us, that explains the relationship between concentration and rate. Between concentration in molarity and rate. What it allows us to do is if we say, okay, we change the concentration of reactant A, what's that going to do to the speed of the reaction? How much will it change it by? If we change the concentration of B, how much will that change how fast the reaction goes by? So the rate law has the general form of this. Rate equals K, and then we put the concentration of each reactant. In this case, we have two reactants. So the concentration of A to the power of X, we don't know what it is yet, we have to figure it out, times the concentration of B to the power of Y. This is the general form for a rate law. Again, it has A and B because we have A and B as reactants. If there was only A, we would get rid of the B here and only have A. This allows us to determine and calculate the concentration of any given reactant for any at any given rate. K is the rate constant. It's a number that is unique to any given reaction. It doesn't change. It's a constant. But it does change for whatever reaction you're applying and working on. So what are our goals? Our goals are to determine the rate law today. We want to be given a set of data, determine the overall rate law. In order to do that, we're going to need to figure out what the rate constant is for a set of data. So we want to make sure we can do these two things at the end of today. So here's the type of data that you'll be given. You have a reaction, okay? Fluorine gas plus 2 moles of ClO2 produces 2 moles of FClO2. What's going on? We did 3 different experiments, okay? We did trial 1, trial 2, and trial 3. And what we're seeing here are the concentrations of each reactant in those trials and the rate, the speed of that reaction in molarity per second. So the question asks us, given the information in the table above, determine the overall rate law of the reaction. So remember our general form of the rate law. Rate equals K times the concentration of our reactants. So which reactants do we have? We have F2. It's going to be to some power of X. And ClO2, which is going to be to some power of Y. A thing to note, the coefficients, in this case a 1 and a 2, have nothing to do with the rate law. The coefficients don't matter. The mole ratio doesn't matter. But what we need to be able to figure out are these 3 things. K, X, and Y. That's our goal. Can we figure out those 3 things? So the first thing that we need to do is we need to figure out how changing the concentrations of one of the reactants affected the rate. So first thing to look for, okay? Trials where the concentration of one reactant did not change is constant. So for example, if I look at trial 1, I notice that the concentration of F2 is 0.1 and concentration of ClO2 is 0.01. If I look at trial 3, I see the concentration of ClO2 is still the same. So in this case, I changed the concentration of F2. What we want to see now is what effect does changing this concentration have on the speed? Does it make it faster? If so, by how much? So the way we need to do this is we need to set up the rate law for both of these trials. So the rate law for trial 3 would be K times the concentration of F2 in trial 3, which is 0.2 to the power of x, times the concentration of Cl2 in trial 3, 0.01 to the power of y. And now I'm going to divide this, okay, essentially, by, I'll make this a little bit neater for us. The same thing, but for the trial where ClO2 didn't change, in this case was rate 1. So it's going to be K times the concentration of F2 in trial 1, which was 0.1 to the x, times the concentration of ClO2, which stayed the same. So now, why was this important? Why did I do this? Well, I can cancel some stuff now. I have K on the top and bottom. Those cancel. I've got to be careful here. Okay? They cancel. So bye-bye K. And also, I have 0.01 to the y on the top and bottom. Those cancel. So what I'm going to be left with is rate 3 divided by rate 1. Well, let's plug in the numbers. The rate of trial 3 was 2.4 times 10 to the negative third over 1.2 times 10 to the negative third. Okay? That's going to be equal to 0.2 to the power of x over 0.1 to the power of x. Now I just got to do a little bit of simplification. 2.4 times 10 to the third divided by 1.2, that's equal to 2. 0.2 divided by 0.1 gives me 2 to the x. So I can clearly see that x must be equal to 1. Boom. This tells me that if I double the concentration of fluorine, it's going to double the rate from 0.1 to 0.2, 1.2 to 2.4. So we would say that this reaction is first order with respect to F2. Now, I don't want you to get bogged down in the math too much because we're going to get a lot of practice with it. But conceptually, what you should be able to see here is when I increased the concentration of fluorine, that made the rate faster. It doubled it when I doubled it. Okay? But now I need to figure out what y is. So let's go ahead and figure out y. We'll do that on the next page. We'll set up the same thing. We need to find the trials where the concentration of ClO2 changed, but the concentration of F2 did not. So here, in trial 1 and 2, the concentration of F2 did not change, but ClO2 did. So I'm going to do rate 2. I usually want to put the bigger number on top, in this case 0.04 over 0.01, because that's going to allow me to just simplify a little bit easier with the math. So I'm going to have times K times the concentration of 0.1 to 1 times 0.04 to the y, because we don't know what it is yet. K times 0.1 to the 1, 0.01 to the y. So what can I cancel? Well, I got K's canceling, 0.1 to the 1 canceling. So if I rewrite this down below, rate 2, the rate in trial 2 was 4.8 times 10 to the negative third. Rate in trial 1, 1.2 times 10 to the negative third is equal to 0.04 to the y over 0.01 to the y. So again, if I simplified this, I would be left with 4.8 divided by 1.2 is 4, equal to 4 to the y. So y, therefore, must equal 1. So we've solved this. We now have seen that this reaction is first order with respect to x and with respect to y. The problem is I'm not quite done, believe it or not. What we've done so far, if we go back to this, our goal was to get this equation. We've gotten y, we've gotten x, but we haven't gotten k yet. So what we have here is rate equals k times the concentration of F2 to the power of 1 times the concentration of ClO2 to the power of 1. What I need to figure out is this. So how do I do that? So, what you should make a note of, in order to determine K, you plug in values that are given in the table for the concentrations and rate. It doesn't matter what trial you use. So, let's go ahead and just choose trial number 1, just because it's the first one. So the concentration of F2 was 0.1. So I'm going to write K times 0.1 to the 1. Concentration of ClO2, 0.01. 0.01 to the 1. And the rate in trial 1 here, 1.2 times 10 to the negative third. So I'm going to write 1.2 times 10 to the negative third. This is just basically algebra at this point. I just have to solve for K. So I have 1.2 times 10 to the negative third equals K times 0.1 times 0.01. So this is going to be equal to 0.1 times 0.01. 0.001 is equal to 1.2 times 10 to the negative 3. So divide by 0.001 on both sides. What I should get for a final answer is that K is equal to 1.2. So now I've solved for all three things. So the overall rate law, my final answer would be rate equals 1.2 times the concentration of F2 times the concentration of ClO2. Boom. That would be the final answer for this problem. Now you might be thinking, oh my gosh, Shar, that is an insane amount of work to do one little problem. It is, I agree, but with enough practice you get the hang of it, and there's also a much faster way to do it, which I will show you in class. For now, I want you to feel comfortable with the long way. Other thing, a few key points about rate laws, okay? So remember, the general form of the rate law is this. Rate equals K times the concentration of one of your reactants to some power times the concentration of another reactant to a different power, okay? The stoichiometry, meaning the coefficients, do not matter. They do not play any role in your rate law. So for example, if we go back, this is our final answer. Ones were the powers here. But if you look at the equation, there was a 2 in front of ClO2. That played no effect. So stoichiometry does not matter when you're determining the rate law. Okay? K can be determined from any trial. We chose trial 1, but we could have chosen trial 2 or trial 3, and we would have got the exact same answer. That's because it's a constant for that reaction. Okay? And last but not least, I can't emphasize this enough. Check your math. The exponents will always come out to nice numbers, either zeros, ones, or twos, maybe threes in this class. If you take more advanced chemistry, they won't be even numbers. But for now, if you get that you get x is equal to like 0.23, you probably made a math error. Double check your math so you don't make any silly mistakes.